Today I'm going to be talking about population parameters of coastal tailed frogs in northwestern California. And I'm going to begin by giving some brief background information on the natural history of tailed frogs. And then I'll talk about some of the methods that we've used to sample these frogs and also launch into some results and talk about some conclusions. So tailed frogs are in the genus Escaphus, and they're specialized for cold, fast-flowing streams. And the tadpoles have sucker-like mouth parts that enable them to cling to rocks in these streams. And then the males have a tail that's used as a copulatory device to transfer sperm internally to the female during mating in streams. Now, mating in tailed frogs is so unique that Seaver coined the term copulexis to describe the combination of amplectic and copulatory mechanisms resulting in internal fertilization in Escaphus, and this is unique to this genus among anurans. So this really illustrates the special adaptations of these frogs for their life in streams. And as Lowell mentioned, tailed frogs are sensitive to timber harvest impacts, especially increases in sediment loads in streams and also increases in stream temperatures. So it's really important, as Lowell also talked about, to monitor the abundance of these frogs over time, especially on a managed landscape. So as far as tailed frog abundance studies go, we're really lacking direct estimates of abundance for adult and immature tailed frogs. The focus of most research, including our own research, has been on the larval life stages, and this is mostly because the larvae are restricted to the stream and they're relatively easier to study, and also, more importantly, they're more vulnerable to the effects of timber harvest because of this restriction to the stream. Oops. Okay, so as Lowell showed you this slide, we have a lot of annual variation in the abundance of the larvae, so it's important to get abundance estimates of the adults to try to help to explain some of this variation. So the objectives of our study was first to estimate abundance of tailed frogs and fixed length reaches using mark recapture, and then we also estimated recapture probabilities. So here's our study area. Again, it's on Green Diamond Resource Company managed timberlands, and you can see those red circles there indicate the location of our study streams. Now in 2002, the first year of this study, we randomly selected 4 study streams out of the 17 that are monitored annually by Green Diamond for tailed frogs. However, unfortunately, 2 of these streams that are outlined here in yellow showed comparatively few captures of frogs that we did not think would be adequate for mark recapture analyses. So in the following 2 years, we substituted 2 new streams that we knew to have fairly good numbers of tailed frogs. So these were nocturnal surveys, and each stream was surveyed year-round with the emphasis on spring, summer, and fall. And we surveyed each stream 2 to 4 times per month, and then once per month when the captures declined in the winter. And our reach lengths varied from 80 to 175 meters, and this depended on stream width. And then we searched the entire length of the reach, first upstream and then back downstream. And these were area-constrained visual encounter surveys, and we located each frog by detection of the eye shine. And then we would, when we saw a frog, we'd capture it and put it in a bag with some creek water, and then we would detain it for marking after completion of the survey. And then all frogs were returned to their capture location after marking. The frogs were marked using visible implant fluorescent elastomer, and they were first anesthetized and then given an individual mark. And one of the great things about doing this study was we got to use this mark recapture technique, and it allowed us to wear these really neat glasses as we were out in the field, and that was a lot of fun. So for data collection, we measured each frog, and then we weighed them and determined sex when possible. And during the breeding season, we were able to collect reproductive data, and we considered males with nuptial pads and gravid females to be reproductive. So as part of my master's research, I did a life history study on these populations, and I estimated size and age classes based on that snout vent length data and reproductive data. So I'll use these age classes in these population analyses. So for the abundance analysis, we used Program Mark, an open population model, and we estimated capture probabilities and apparent survival. but I'm only going to focus on capture probabilities for the purposes of this talk. So candidate models were ranked using AIC, and we performed bootstrap goodness of fit tests to test the fit of the global model. And then I also used that test to estimate C-hat to correct for over-dispersion in the data. Oops. So the covariates in this analysis were creek, sex, age class, time, and a linear time trend and a quadratic time trend. So we used combinations of these covariates to construct various candidate models. And for our abundance estimator, we estimated frog abundance using the Horvitz-Thompson type population estimator. And we estimated abundance over all summer surveys for only Bald Mountain and Lower Jiggs Creeks, and I'll talk more about why we only included those creeks a little bit later. So what this formula does is it takes, for a particular occasion, it sums up 1 over the capture probability for each frog that was captured. And that'll give you an estimate of abundance for a particular occasion, and then those abundance estimates can be averaged over all occasions. So now I'll talk about some of my results, or some of our results, excuse me. So this is a capture summary of all creeks in all years. And my main point with this slide is that you can see that in Bald Mountain and Lower Jiggs Creeks, we captured the most amount of frogs. And in fact, these were the only creeks that we were able to get population estimates or abundance estimates for. The other creeks just appeared not to have enough captures to work in the mark recapture analysis. So it appears that for at least these creeks, we needed about 300 frogs to get good estimates. And we captured significantly more frogs in the summer, so that was the season in which we had adequate captures to estimate abundance. So here are the results for 2003. These are the top 7 models out of a total of 52 candidate models. And you can see that the top 2 models support a constant capture probability over time. And these are the estimates from the top model. Capture probabilities were estimated to be about 6%, which is a relatively low capture probability. Oops, excuse me. And just keep in mind that this means that capture probabilities were thought to be constant over time, and they did not vary by age, sex, time, or creek. And in 2004, the top models supported a different combination of covariates for a capture. We could have an interaction between age and quadratic time, and this combination of covariates came up in the top 6 models. And estimates from the top model are showing for adults about 10% of capture probability, and for immatures about 12%. So it appears as though the capture probabilities were a little bit higher in 2004. So here's that quadratic time trend. And if you'll look here, the adults relative to the immatures, the capture probabilities appear to decrease more than they do for the immatures, especially in here in the middle of the summer. And then they increase towards the end of the summer and approaching fall. So there could be a lot of potential explanations for this. But what we think might best explain it is that during this period in the middle of the summer, the adults might actually be breeding and in the stream and not available for capture, and therefore would have lower capture probabilities. And this could also explain why we had different top models for capture probabilities among the years, because in my master's thesis research, it indicated that females may breed every other year, so there may be a different number of breeding adults from year to year. Oops. So here are the abundance estimates for over all capture occasions. Those are capture occasions on the x-axis for each year and for each stream. And the main thing I wanted to show here is that there's a lot of variation in these abundance estimates, not only within the year, but also among years. So here are those estimates averaged for males and females over all capture occasions. And what we wanted to do with these abundance estimates was divide these estimates for males and females by the reach length and get an estimate of number of frogs per meter of stream. And then we could take these estimates and multiply them by the total potential habitat and length of stream that could potentially support tailed frogs. So in order to get the potential habitat measurement, we use GIS along the main stream, or excuse me, the main stem of each stream to get a linear meter of the amount of stream that might potentially support tailed frogs. So our estimate for Jiggs Creek was 2,630 meters that could potentially support tailed frogs, and 8,770 meters for Bald Mountain Creek. So here's some of those extrapolations, multiplying the potential habitat times frogs per meter. And you can see that in Lower Jiggs Creek, we're estimating about 6,000 frogs potentially in that entire watershed, and about 42,000 frogs in Bald Mountain Creek. Now I want to make it clear, I know these are big numbers, that this actually assumes that the frogs per meter is constant throughout that watershed, which would lead to an overestimate. However, we only included the main stem in our total habitat, so we're hoping that that'll balance it out a little bit. And at the very least, this suggests that there's a potential for thousands of frogs in these streams. Oh, I also wanted to point out the females here, because of course the females are what we're most interested in because they're the ones that produce the larvae. And this estimate even suggests that there's thousands of females in these streams, potentially. And for some conclusions, so these abundance estimates indicate that tailed frogs have the potential to be a major component of headwater streams. However, we were only able to estimate abundance for 2 streams with relatively high frog captures. Now, it's 2 streams out of a total of 6 streams, and there's capture probabilities were relatively low. So in those 4 streams with low captures of frogs, with low capture probabilities, it's difficult to get an estimate. So there's really a need for increasing capture probabilities or captures in streams with low densities. So here's some suggestions on how to do that. The first thing you might think of is you could increase the number of observers, and you could also increase the amount of stream that you searched. And the other thing you could do is you could use a variety of search methods. You could use binoculars in conjunction with the naked eye to detect eye shine. And you could also use spotlight surveys, and these could be used in combination. You could also use drift fences and pitfall traps along the banks to catch frogs that are not just in the stream channel, but also dispersing up out of the stream channel and onto the banks. And then, of course, you can increase the frequency and or the number of surveys of each stream. Now, another thing I wanted to point out is that amphibians typically have low capture probabilities, less than 10%, and we certainly see that with these frogs in this study. And this is thought to be, at least in part, due to only a fraction of the populations are actually available for capture at any given survey. And this has been documented for tailed frogs in Montana, at least for Escapus montanus, that only a fraction of those frogs were thought to be active on a given night. And this could be due to foraging cycles or some other behavior. And in order to take this into account, this could lead to temporary immigration. You could use a robust design to actually get at that temporary immigration. The robust design combines an open and closed population model, and it gives you estimates of detection probabilities and also temporary immigration. And you can also get abundance estimates. And the reason we didn't use a design like this is because we also wanted to characterize the life history of these populations and look at their activity throughout the year, so we did year-round surveys. But I think that this robust design would be something that would work a little bit better, and it might be something that we'll implement in future studies. And I think that, okay, just real quick, wanted to acknowledge Green Diamond Resource Company for funding this study and all of the people who have participated, and that's it. Thank you.